slippery. Very slippery.
Hello, and welcome to episode 34 in our series on Vertex Operator Algebras. Today, we are following up on our conversation of quantum mechanics with a bit of applied representation theory. Indeed, today's discussion will be all about the special linear group in 2 dimensions and its relationship to the special unitary Lie group, SU2. Let's dive in. Last time, we discussed how the physical states are represented formally with a Hilbert space, and how observables are self-adjoint linear operators on such a space. Hilbert spaces, you might recall, are linear spaces equipped with an inner product that serves double duty as the metric, together with the requirement that the space is complete as a metric space. This inner product, of course, defines what we mean by self-adjoint implicitly. In particular, we discussed how the algebra of these self-adjoint operators was a Heisenberg algebra, and how the Hilbert space subsequently inherited the structure of a Heisenberg module. Today's lecture will explore a different set of operators on these Hilbert spaces, an operator algebra reflecting the symmetries of a physical system. If you've been following our series, you might recall Noether's theorem, which related the symmetries of a physical system to conservation laws. We discussed that in detail in section 31. Now that we know a bit more about the machinery of quantum mechanics, you might ask, how does Noether's theorem apply more directly to quantum theory? Well, long story short, these symmetries are encoded in an algebra of unitary operators on the Hilbert space. Let's recall some quick facts about operator algebras. The self-adjoint operators, whose spectra represent physical observations, were defined in terms of the inner product. Here we see that the inner product of psi with h psi is equivalent to h psi with psi. H, in other words, doesn't care which side of the inner product it's on. Because a physical Hilbert space is typically a complex one, this, amongst other things, implies that there's a spectrum of eigenvalues that are real numbers. Operators that reflect a symmetry of the physical system are unitary, which is to say that the inner product of psi with phi is equivalent to the inner product of the transformed vectors u psi with u phi, which suggests that the adjoint of u is equal to its inverse. U here, of course, being an operator on the Hilbert space. Compare this with the self-adjoint operator h, whose adjoint equals h itself. Now, assuming the operators u reflect a symmetry of the physical system, the Hilbert space must possess the structure of a representation of u. But what might that look like? Well, first, as the spectra of h are real numbers, the spectra of u are akin to complex phases. Indeed, a phase rotation e to the I theta is the prototypical unitary operator. So much so, in fact, that the phase angle theta, that can be interpreted as a, say, non-trivial circle bundle over spacetime, can be understood as the theory of electromagnetism. Now, how might we generalize a transformation by a complex scalar? Perhaps into something non-abelian? The study of matrix Lie groups gives us plenty of examples. Indeed, there's a whole series of unitary matrices of rank n, whose adjoint, the transpose complex conjugate, is equal to its inverse. This series of so-called special unitary matrices, or SUN, has the requisite form, which you might recall tangentially from the study of the Baker-Campbell-Hausdorff theorem. The idea here is that the local object, the exponentiated operator O in this case, is a member of the Lie algebra SL2C, that is, those traceless matrices over the complex numbers with determinant 1. Now, before we dive too much into the representation theory of SU2, let's first give some physical motivation. Consider a constant, uniform magnetic field directed upwards. You might recall from elementary physics that magnets tend to align with such a magnetic field, and they do so because of a torque that pulls them towards alignment. Now, as it turns out, particles tend to have tiny little magnetic moments. Particles like electrons or neutrons or even silver atoms do. An imprecise but perhaps historical way to think about these things are little loops of current. The point is, their own tiny magnetic fields are also vectors with a specific direction. For reasons related to that imprecise analogy, we often call these magnets spins. The energy of these little particles, behaving as little magnets, is simply the standard three-dimensional dot product of the constant magnetic vector B with the orientation of these little magnets, or spins, S. Note the presence of the minus sign, which ensures that the lowest energy state is the one where the spins all align with B, and the highest energy state is the one where they have opposite signs. If having a negative energy is something that bothers you, feel free to add a constant term to the energy operator H. Now, these little spins, be they electrons or silver atoms or what have you, are quantum mechanical objects. They have specific states which belong to the Hilbert space. And as it will turn out, the energy eigenvalues of H will be plus or minus a constant, h bar over 2 times the magnitude of B. Incidentally, that's the same h bar from our discussion of the harmonic oscillator last time. Now, I will always mess up the minus signs in these calculations, so just so we're clear, there are 2 states here. There's an up or positive state and a down or negative state. They have equal but opposite energy eigenvalues. What's important here is that we have a 2-level system, and such a 2-level description of a given system is often called a doublet representation, for obvious reasons. Now, back to the representation theory. The Lie algebra SL2 is, of course, a linear space itself, and a basis for it can be written out explicitly in terms of 3 matrices, commonly represented by the sigma 1, sigma 2, and sigma 3. As you can readily verify, these are all traceless with unit determinant. Note the particular role played by sigma 3, the diagonal one, whose eigenvalues are plus or minus 1, who implicitly kind of defines a basis for the representation to come. The vector of spin operators S is given by h bar by 2 times these sigma matrices. And note the purposeful confusion of the physical 3-dimensional vector space with the Lie algebra of vector components. This technical confusion begets a long story of intellectual confusion, a story definitely worth telling, but for our purposes here, we'll just focus on the math. Note that the eigenvalues of all these matrices are the same, so the eigenvalues of all 3 components of the vector operator S are plus or minus h bar over 2. The components of these vectors satisfy a Lie bracket, where epsilon ijk represents the totally antisymmetric object with 3 3-dimensional indices. Great. We've described the Lie algebra. Now let's exponentiate it and explore the Lie group. The unitary operator we've been aiming at, u, is written e to the I s dot b, or if you like, e to the I h, where h is the energy operator. Indeed, any such unitary operator can be represented as e to the I h for some self-adjoint operator h. So the adjoint of u is clearly the inverse. A note for the mathematicians: it's traditional in mathematics circles to represent the operator as simply h without the I. Now, the spin up or down states can be transformed by these kinds of operators u. Unlike the Heisenberg group, SU2 is compact, which will make our representation discussions much simpler. Indeed, representations of SU2, the structure of our Hilbert space of states, will be semi-simple, which, for our purposes anyway, means finite. We might compare that finiteness, for example, to the infinite tower of states in the Heisenberg modules we've been discussing, where the ground state could be augmented by a ladder operator, and the physical states are essentially indexed by powers of eta bar. This allowed us to speak about things like the lowest weight representation, with the state of lowest weight, or energy, being the ground state. For the SU2 case, we can build similar operators, which we'll call sigma plus or minus, by giving the eponymous linear combinations of sigma 1 and I times sigma 2. These are given by the simple explicit forms, which you might try to verify as a simple exercise. To see how these apply to the doublet states we've been talking about, consider the application of sigma plus to the column vector 0, 1, which you might call the spin down state. Here, some simple algebra reveals that the sigma plus acts as a ladder operator, taking you from spin down to spin up. Note that sigma plus acting on the spin up vector brings you to 0, whence our discussion of finite representations. So we see that there are precisely two eigenstates, spin down and spin up. Which should have been obvious, of course, given that we assumed a two-dimensional linear space. You can, of course, build a similar structure with sigma minus. These give us two complementary perspectives, a highest weight and a lowest weight one. The representation is a convention, and it depends on which of the sigma plus or minus you want to take as your fundamental ladder operator. We can, of course, consider other representations in other dimensions, keeping the algebra the same, and we'll see those representations will have a similar structure, indexed by powers of whatever form of sigma plus happens to be in that representation. The quickest way to build higher dimensional irreducible representations is to consider tensor products of these doublets. Keeping in mind our two basis vectors for the space of states plus or minus, let's consider a tensor product of two copies of the doublet. This simple tensor product, of course, decomposes into symmetric and antisymmetric parts, which individually are irreducible representations of SU2. By symmetric, of course, we mean the discrete symmetry that exchanges the labels of those vectors, which is left and right, if you like. Antisymmetric is defined as you'd expect. Let's see what that looks like explicitly. The symmetric representation is easy enough to think about. Clearly, if both spins are up or positive, the state is symmetric under the exchange of those two vectors. The same is true if they're both spin down. The non-trivial case is if one is spin up and the other is spin down, which we can make into a symmetric state by manifestly combining them in a symmetric way. This, of course, also motivates the antisymmetric representation. So we're left with a triplet and a singlet. So let's look at them as lowest weight representations using sigma plus. For the symmetric case, let's consider the down-down symmetric state, and let's act on it with sigma plus. In this context, sigma plus will act as a derivation with respect to the tensor product algebra structure. This brings us to the mixed symmetric state, which also affords us an additional action of sigma plus, which brings us back to the up state, where any further action by sigma plus will naturally map the top state to 0. Put differently, we have a triplet of states connected from lowest to highest weight, or spin eigenvalue, by sequential operation of sigma plus. The spectrum of the energy operator in this case gives you h bar times 1, 0, or minus 1. There's really only one non-trivial way to consider an antisymmetric combination of two things, and the associated spectrum will include the single eigenvalue, 0, which you can compute explicitly as an exercise. We can continue this to form a triple tensor product, although this starts to get tricky because you can't anti-symmetrize more than two things in two dimensions. But again, we find two kinds of irreducible representations of three doublets, one of 4 dimensions and one in 2 dimensions, each state of which is again connected by the action of sigma plus. If you study the representation theory of Lie algebras, you might run into the mnemonic use of the Young tableau, which gives you a calculus that can make these kinds of computations relatively simple to do. But that's another story for another course for another day. Now, all this is well and good and hopefully reasonable if it's a quick review, but it's worth pointing out that these representations have important physical consequences. Quantum mechanics, as it turns out, organizes itself into irreducible representations of any relevant symmetry algebras. And the SU2 symmetry, which descends from the three-dimensional rotational invariance of real three-dimensional space, is no different. That is to say, the physical system represented by spins in a magnetic field only has a finite set of options for each energy level. It is quantum mechanics, after all. So, let's see how this works in practice. Take, for example, silver atoms. silver atoms form a spin doublet, which can take the state of either spin up or spin down. Let's consider a little machine that spits out a beam of silver atoms. This beam can be pointed in a given direction, but the spin vector of any given atom turns out to be pointed in any wild direction along the beam. It's random, it's thermal. We can measure the direction of the spin using a machine that was first developed by German physicists Otto Stern and Walter Gerlach, which imposes a sudden sharp magnetic field to kick the spins according to how their spin direction aligns with the magnetic field. If the spins were really allowed to take any configuration, we'd expect to see them collect as a smear distribution, a histogram of counts, if you like, with a peak around 0, a typical average. This is the so-called classical case. This would be what you'd expect to see, for example, if you were throwing frisbees or some other kind of macroscopic object. Of course, this is quantum mechanics, so what we actually find in the physical world, in real life, is two sharp peaks, one near plus or minus h bar over 2. Indeed, the results of the original experiment implied just this, and you can see clearly the difference of the measured beam with the magnetic field when it was first switched off and then switched on. The beam splits clearly, if cleanly, into two parts. Meaning, no matter what, you can't measure a value of spin 0 from a system that's in a spin doublet. You can't measure a value of 0.1 or 0.001 or 1.2 or minus 0.445. Nothing like that. You can just measure plus or minus h bar over 2. Hey, it's quantum mechanics. And that's our show. And that's also the end of our long digression from the FLM text. Next time, we're going to crack open Chapter 3 and take a look at the affine Lie algebra associated to the little beast that we've been discussing today, SL2. See you next time.